Can you see now?
Okay, ma'am. Let me
Okay. All right. And you can see my PPT now too?
Yes, ma'am.
Okay. So, so light, as I told you, that discrepancies in the experimental observations of Newton's corpuscular, using Newton's corpuscular theory, led to the establishment of the experimental observations and theories put forward by Thomas Young and Christian Huygens and Fresnel and etc. And over several years and several experimental observations, it was established that light was a form of wave. And then finally, in the late, late 19th century, you know that Maxwell gave his 4 equations, which sort of unified the entire electromagnetic wave family, and it was firmly established that light was a form of wave. All right, but then at this time again, sorry, but then at this time again, there were some new experiments or new aspects being studied for some older experiments that gave results that could not be explained using the wave nature of light. All right, so the first, so this is what I am saying when I say that the first step were failures, which were the pillars of success of establishing the quantum theory, the new theory. So the first of this was an effort to explain black body radiation, right? You all know what a black body is. You all know what we define as a black body. You have studied it, I think, in your class 12 thermodynamics and heat, that when there is a body which absorbs all kinds of radiation that fall on it, we call it a black body. So an ideal black body, or an ideal black body is an ideal concept, but you can go close to a black body by taking a sort of sphere, making a small hole on the surface and painting the entire inner surface of the sphere by um, lamp black or soot, so that this kind of a sphere, so that through this perforation in the sphere, all the radiation that goes in will be absorbed, and then when left by itself, it will radiate radiations of all wavelengths. All right, this is what is a perfect black body. Now, when the radiation coming out from this perfect black body was studied, it was seen that it did not obey the rules that would be followed by radiation if it were a form of wave. All right, so considering radiation as a wave did not explain how the behavior of the radiation coming out from a black body was with changing frequency. All right, ideally, if you increase the frequency of a radiation, then its intensity should increase. But in the black body radiation, it was seen that as frequency was increased, the intensity increased up to a certain point, and then it started decreasing. I'll show you a picture from Iceberg and Resnick's book, where it is shown. Can you see the picture? Can you see the picture? This
No, ma'am.
graph here, this graph here, I have put
No,
on
ma'am.
my
No,
camera. You have to look at the window where uh,
no, ma'am. আপনি ম্যাম শুধু স্ক্রিনটা শেয়ার করে রাখছেন, ওই জন্য শুধু ছবিটা ওখানে ছোট করে দেখা যাচ্ছে। মানে আপনার ওখানে ছোট করে দেখা যাচ্ছে কিন্তু স্ক্রিনে আসছে না।
আচ্ছা আমি তাহলে দাঁড়াও নেট থেকে দেখানোর চেষ্টা করছি। দাঁড়াও আমি নেট থেকে দেখানোর চেষ্টা করছি। Can you see the picture here? This graph?
Yes, ma'am.
Okay. So
Yes, ma'am.
this is what I was talking of when I was talking about a black body. So see, this is a cavity. It is also called cavity radiation. So this is a cavity which has been painted black on all sides. And this is a small perforation. And the perforation is such that the radiation enters it and then it gets reflected from all the walls of this cavity. See, it undergoes multiple reflection from the walls of the cavity, and then when it comes out, it contains all kinds of wavelengths. All right. So ideally, with increasing frequency, the radiation power should increase. But it was found that with increasing frequency, it first increased and then decreased. So there was a maximum that it reached and then it decreased. And this peak value increased. This peak value became more and more with increasing temperature. All right. As you can see, with increasing temperature, the peak value increased. So this could not in any way be explained using the radiation theory of light. All right. Why it could not be explained, you will do in details in BM Sir's class. So there were several people who gave an explanation mathematically to this observation, that why there was a peak and then again the radiation power decreased with increasing frequency instead of steadily increasing with increasing frequency. First of all, there was Wien's radiation formula. Now this formula was in agreement at higher wavelength, but it did not agree for lower wavelength. Then there was Rayleigh-Jean's law, which agreed at lower wavelength, but as you went to higher wavelengths, it did not, it went to infinite values, and that was called ultraviolet catastrophe. It was these failures that led Planck, and here I have given a picture of Planck because he, you can say, is the father of quantum mechanics, although he did not himself formulate quantum mechanics, but he was the first person who gave a hint of the existence of quantum mechanics, although he himself did not believe in it, and I'll tell you the story a little later. So he put forward the quantum theory of radiation. Okay, and just wait a minute, I'll tell you what he actually said. Just give
হ্যালো ম্যাম, আপনার এখন শোনা যাচ্ছে না ম্যাম?
একটু ওয়েট করো, আমি একটা জাস্ট কাজ করে আসছি, আমাকে 2 মিনিট দাও একটু।
ওকে ম্যাম।
Yeah, so I'm back. All right. Okay. So what did Planck say? Planck said that inside the cavity, this was a sort of ad hoc assumption by Planck. He just said that when inside the cavity, when the radiation is bouncing back from the walls of the cavity, it is not doing so as a continuous process, but it is doing so in groups of particles that he called quanta of energy. And as you know, each quanta is now known as a photon. Okay, and okay, so each quanta is now known as a photon, and um, he said that it is only during the exchange of energy with the wall of the cavity that the exchange of photon takes place. Otherwise, the radiation is a wave, just like we know, right? And he gave the energy of each such photon as h nu. All right, when nu is the frequency of the radiation and h is a very small number, which is known as Planck constant. Can anyone tell me the value of Planck constant? Anyone?
Ma'am, it is 6.6 into 10 to the power minus 34 joule second.
Yes. So this 10 to the power minus 34 is very important. Now, when we deal with Planck constant a lot, we tend to, overlook this value, 10 to the power minus 34. But this 10 to the power minus 34 value makes all the difference. It's a, as you can understand, that it is an extremely small number, very small. 10 to the power minus 34 is, unthinkably small a number. All right. And so Planck was a very stringent classical physicist. He did not believe in quantization. He only saw that his mathematics gets a little boost up if he uses these small quanta of energy that are being exchanged between radiation and wall of the cavity, and using this small twerking of the theory helps him in explaining black body radiation, so that the graphs that are obtained experimentally can now be explained theoretically. Okay, if he takes the radiation to be made up of small quanta of energy when they are exchanging the energy with the walls, then he can give it a statistical treatment, and using the statistical treatment, the observed graph of why it first increases and then it decreases with frequency can be satisfactorily explained. He was okay with this theory only because of the smallness of h. Because when something is of the order of 10 to the power minus 34, under all macroscopic circumstances, you can consider it to be as good as zero. All right. And I'm repeatedly, I might repeat this several times in our future discussions also, that the smallness of h was what make all the difference. Okay. And this was the first case where radiation was thought to be quantized, even though quantum mechanics was far away. Planck only used this small sort of, what should I say, substitution of the wave nature by a quantized energy packet behavior during exchange, and this was the first step of quantum theory of radiation. All right. And that was that. Light was still thought of as a wave, electromagnetic wave. All right. Now then, Now then, several years after Planck gave his quantum theory of radiation to explain black body radiation, there was this another experiment called photoelectric effect observed by Einstein, where he saw that when light falls on metals, electrons come out. And as you have studied in your plus 2 also, and you're going to study in detail in the quantum theory part also, that the way these electrons come out, the intensity of these scattered electrons from the metal surface due to light falling on it, they did not obey the nature that would have happened if light behaved as a wave. All right. So, using the wave theory of light, the experimental observation regarding photoelectric effect could not be explained. On the other hand, when Einstein, uh, sort of recapitulated Planck's photon theory and said that when light was falling on the metal surface, it actually behaved as a group of particles, packets of energy, and these photons collided with the surface electrons and knocked them off the surface of the metals, then the experimental observation of photoelectric effect was perfectly matched. Similarly, there is another phenomenon called Compton scattering, where also I'll show you again what Compton scattering is. Just a second. I mean, you all can do this by yourself. I'm just googling out, but showing a picture helps when I'm explaining something. Okay. So you see, in Compton effect, actually, I want to show you the graph. Yes. Okay. So if you see this graph over here, you see the intensity is plotted with wavelength, and ideally, I mean, if light were just a wave, then with increasing wavelength there would be an increase in intensity, but instead it was seen that there were two peaks observed at two different wavelengths. All right, and this was explained only when it was this the when light was thought of as a particle instead of a wave. What was done? This is the wave, but actually this is the wave where it was assumed that there were particles each of energy h nu. And okay, so what happened is, when such a photon came and collided with an electron, the electron was scattered in one direction and the photon was scattered in another direction with a reduced wavelength. All right, and it is because of this, see, they have shown here the GIF image also, the photon. Can you see the GIF image?
Yes, ma'am.
Yes, ma'am.
Can you all see the, yes. So see, the photon is coming and sort of knocking off an electron from one of the shells. The electron gets scattered in one direction and the photon gets scattered in another direction, but now you see they have shown a change in color from yellow to red to show you that it is with a different wavelength. All right, and this is very easily explained using particle nature of light. It is simply a collision theory where you apply conservation of momentum. It becomes very simple explanation of Compton theory. So once black body radiation was explained by Planck using the photon concept of wave, other experimental observations like photoelectric effect and Compton scattering were explained using particle nature of light. All right. Now, while light was being established as not only a wave phenomena but also a particle phenomena, so that you can say that, but you can't deny the fact that light does behave as a wave in incidents of interference and diffraction and polarization. So it was now understood that light behaved not only as a wave but also as a particle, but under different circumstances. So in other words, it had dual nature. The same electromagnetic radiation can show its wave nature under certain circumstances, and it can show its particle nature under certain other circumstances. In general, we can say that when light interacts with light, we get to see the wave nature, like in interference, diffraction, etc. And when light interacts with matter, we get to see the particle nature, like in cavity radiation, photoelectric effect, Compton scattering. Now, is this dual nature true for light alone? No, because when these things were being studied, there was a person called Prince Louis de Broglie who actually went to study medicine, but who became so interested in his brother's study of the particle nature of light that he began studying physics himself, all right? And he saw that if light were to have a dual nature, so must be the case of matter. Matter must also have a dual nature. It cannot be exclusive for light itself. So he gave a theory or a hypothesis, which is known as de Broglie's hypothesis, where he said that every particle, every moving particle will have associated with it a wave. Okay, so, and he gave a formula for the wavelength of such a wave also, later known as matter waves. So initially it was in the theory form, but later in several experiments, out of which there is Davison-Germer experiment, there is Stern-Gerlach experiment, where it was seen that electrons, when they are made to fall on crystals, the outcome, the intensity, is like a diffraction pattern, all right, which is possible only for waves. A particle cannot show diffraction pattern because you cannot apply the principle of superposition on discrete particles. So it was, but it could be explained when electrons could be thought of as waves and the diffraction pattern could be explained. Same in Stern-Gerlach experiment. It could be explained only when the electrons were thought of as waves. So such experiments showed that matter under certain circumstances can behave as waves. So when we think of radiation to be behaving as matter, we say each such particle is made up of energy h nu. And when we say matter is behaving as a wave, we say that the momentum of that moving particle is of the form h by lambda, where lambda is the wavelength of the associated wave. And this whole thing is summarized as wave-particle duality. So it is not only that light has dual nature, radiation as well as matter, of which universe is made. You know that universe is made up of essentially two things, matter and radiation, and both can have dual character, wave and particle, and this is summarized as wave-particle duality. However, we must remember that you cannot observe both the characters simultaneously in a single experiment. If you are performing an experiment with radiation and it is showing you wave nature, you cannot in the same experiment see its particle nature. On the other hand, if you are doing an experiment where you are observing the particle nature of radiation, you cannot in the same experiment observe its wave nature. All right. So in general, this is called wave particle duality. All right. So what is the evidence of wave particle duality? As I told you, interaction of radiation with radiation, that is interference, diffraction, etc., is explained by wave nature. Whereas interference of radiation with matter, like photoelectric effect and Compton effect, is explained by particle nature. So which is giving you the dual nature of light. This is Compton effect, this is photoelectric effect. All right. On the other hand, electron diffraction, interference of matter waves, these are the evidence of wave properties of matter. The earlier was particle nature of wave or dual character of light. Now, particle nature of matter we are all aware of, right? We have done Newtonian mechanics for so long. We have done classical mechanics for so long. All we do is, form an equation of motion, write down the Newton's second law, and then find out its equation of motion. So that if we know the position of a particle at one point of time, we can use the equation of motion to track its trajectory and find its position at some other point of time. We did not know how to find the wave property of matter, but now we can see that there are experiments where we can actually see the wave nature of matter too. Now you might ask me that if there is a wave associated with matter, then why don't we ever see it? For example, if you are watching a cricket match and there is a fast bowler who is কে এখন এখন সবথেকে জোরে কে বল করে আমি জানি না, আমি এখন আর ক্রিকেট দেখি না। কে এখন সবথেকে ফাস্ট বল করে? আরে তোমরাও কি ক্রিকেট দেখো না? হ্যাঁ, যা বাবা, কেউ বলছেই না।
অনেকজন আছে।
অনেকজন আছে?
হ্যাঁ।
ও আচ্ছা আচ্ছা, ঠিক আছে, ধরে নিলাম কোনো একজন এক্স ভীষণ জোরে, আমাদের সময় যেমন শোয়েব আক্তার খুব জোরে বল করতো, শোয়েব আক্তার, তার আগে ওয়াসিম আকরাম, এরা সব প্রচণ্ড জোরে বল করতো। শোয়েব আক্তার তো বোধহয় কত 120 কিলোমিটার পার আওয়ার এরকম স্পিডে বোধহয় বল করতো। তো why I'm saying, or maybe suppose you can take the example of Usain Bolt. Usain Bolt is the fastest runner. Now when these people, when they move so fast, or when a ball moves with such a high velocity, then why don't we see a wave associated with it? What happens to the wave? Okay, now you'll get the answer if you look at this formula here. The momentum is h by lambda. All right, so lambda should be h by p. Now h, you know, is such a small number, 10 to the power minus 34, and p, when it comes to the denominator, it would contain mass and velocity. Now mass of any macroscopic particle, be it of Usain Bolt, be it of a cricket ball or a tennis ball, will be in terms of kg, right? Will be of the order of kgs. So we have a pretty large number in the denominator and a pretty extremely small number in the numerator. So you can see lambda would be very, very small. Now, how do we see a wave? We cannot, even for light, when light travels from the source to an object and then gets reflected and comes to our eyes, do we actually see the sine wave passing through air? We don't, right? We observe wave nature of light in certain phenomena like interference, like diffraction. So we see patterns, and we have all analyzed how we see these patterns, how we see the dark and bright patches. So in order to see this wave associated with a fast moving ball, or associated with a very fast of the fastest athlete in the world, or even the fast moving stars and astronomical bodies, you would have to observe interference or diffraction patterns where there is a change in intensity related to this wave associated with the particle. Now, the wavelength is so small that you do not get to observe these phenomena. In order to observe interference or diffraction, you need to have slits which are as small as this wavelength, and you do not get such slits. On the other hand, if you are talking about a fast moving electron, you see, then the mass in the denominator becomes itself very small, and then you get lambda of the order of nanometers. And then if you have a crystal where the interatomic space is of the order of nanometers too, then that behaves as a grating of some sort or slits of some sort, which can show you the interference or diffraction pattern involving the waves related to an electron. Is this clear to all of you why we cannot see matter waves so frequently as we can see light waves? Do you want me to explain it once more, or is this clear to you? একটু কেউ আনমিউট করে বলো। হ্যাঁ,
Ma'am, please
all right,
repeat once.
repeat once. Okay, what I'm trying to say is that when I'm saying that light behaves as a wave and light behaves as a particle, okay, so dual nature, we have all seen interference, diffraction, etc., and we have also heard about photoelectric effect, quantum scattering, etc. So dual nature of light is established. Now when I say matter also behaves dually, now we all know particle nature of matter, there is no doubt about that. How do I establish the wave nature of matter? We have established wave nature of matter using electrons and neutrons, experiments when we take subatomic particles. But then why don't, if de Broglie says, Louis de Broglie, he says that such waves are associated with all kinds of moving objects, then why don't we see a wave associated with a very fast moving ball or a very fast moving athlete? Where does the wave go? Now, first thing you have to understand when you are thinking in this manner is that you do not really see a wave. Even when you are talking about radiation, about light, you don't see the sine wave coming out from the source of light, do you? Do you see a sine wave coming out from the
No,
source of
ma'am.
light? No. Then how do you know it is a wave? Because we have shown mathematically in our physical optics classes that when the two waves interfere with each other in some way or the other, then we get light and dark patches of intensity on the screen. And from the intensity pattern, we can explain that the two waves by superposition give us constructive and destructive interference, and we get under certain circumstances diffraction pattern or intensity pattern, and that is how we say that these are waves, right? Now in the same manner, the waves associated with matter, if we could show that they are showing interference or diffraction patterns, then we would be happily saying that okay, there are waves associated with these moving objects. But this can be seen only in subatomic particles. Why not in macroscopic particles? For that you have to look at this formula. Momentum is h by lambda. So lambda wavelength is h by momentum. Now this momentum contains mass and velocity. So high velocity, and for a ball or an athlete, the mass would be of the order of kgs, a few grams or a few kgs. So it's a very small number, Planck's constant, divided by a very large number. So lambda is extremely small. All right. So we have waves of very, very small wavelength. Now we know that for interference to take place or for diffraction to take place, the slit width must be of the order of the wavelength of the associated wave. Now you cannot get slits of such order. This lambda is so small. It is even smaller than nanometer. It is a few 10 to the power minus something nanometer. You cannot get slits of that dimension. All right. So you cannot see the wave phenomena for waves associated with macroscopic particles. On the other hand, if you take an electron or a neutron or a neutrino, subatomic particles, then lambda equal to h by p and p equal to mv. So the m, the mass, is very, very small. For an electron, it is of the order of 10 to the power minus 20 or something like that. So then you get lambda of the order of nanometers or angstroms. And then if you take a crystal, say, where the distance between two adjacent atoms is also of the order of nanometers, then these spaces between atoms can act as slits. It can act as a diffraction grating. And then the wave associated with the electrons that are interacting with this crystal, they can undergo diffraction from this crystal, and you can actually observe that diffraction pattern and say that yes, there is a wave associated with the electron which is being scattered by the crystal and which is giving us the diffraction pattern. Okay, now is it clear?
Yes, ma'am.
Okay, all right. So Einstein first formulated the photon nature of, formally he gave the photon nature of light. Like Planck said, the photon nature existed, the wave, the packets of energy existed only when there is exchange of energy between radiation and the wall of the cavity. But Einstein said in 1905 that no, this photon nature was persistent all the time. Light is formed of photons. Under certain circumstances, we see the existence of photons. Under other circumstances, we see the existence of the wave nature. So he said light consists of packets of energy of value h nu, where this is the value of h. And what are the properties of photons? The relation between energy and frequency is like this. Now, if it is moving with relativistic speed, then we can write the energy as p square c square plus m0 square c to the power 4, where m0 is the rest mass. Now, for photon, rest mass is 0. They do not have any rest mass because they are moving all the time. So E is equal to Pc, and then you get P is equal to h by lambda using Pc equal to h nu. So E equal to h nu as well as P equal to h by lambda, wave nature and particle nature are established for photons, and this was done by Einstein. So so wave and particle nature of radiation. On the other hand, matter waves was established by Prince Louis de Broglie. See, much later. Einstein did this in 1905. Louis de Broglie did this in 1923. He said that it is not only for radiation. All particles in motion have properties characteristic of waves. The wavelength and frequency of the wave associated with the particle in motion are lambda equal to h by p and nu equal to e by h. But this was only theoretical. There was prediction according to this theory that interference and diffraction should be observed for matter waves. And later on in the Davison-Germer experiment, it was actually observed. Okay, so these are electrons coming from an electron gun falling on a nickel crystal and scattered, and the scattered detector, the detector, when you see the intensity versus the angle of this detector phi, you see this is the nature of the graph that is observed. Now this is possible only when this peak is possible only if electron waves exist. Peaks cannot be observed with particles because particles do not undergo superposition principle. They do not follow superposition of principle. Okay, so interference using thin film samples was done by J.P. Thomson. There was double slit interference using helium atoms and rubidium particles, etc. All right. So what is the course of action now? If you have a moving particle, now this is where we are entering into the realm of quantum mechanics. Okay, it is from this slide onwards that we are going to actually study in our module. So when you are saying that there is a wave associated with a particle, interestingly, I'll just tell you one thing, one story before I move on, that see, Sir J.P. Thomson, he actually established the wave nature of electron, and it is very intriguing because electron was discovered by J.J. Thomson, right? All of you know this. J.J. Thomson discovered electron in 1897. Okay, he discovered the particle called electron, which showed that atoms are not undivided, not they can be divided in further into particles, and he characterized the particle had a definite size, and he showed the charge to mass ratio. J.J. Thomson, he was the father. He did this in 1897. His son is J.P. Thomson, and remember, J.J. Thomson got a Nobel Prize for discovering electron as a particle. His son J.P. Thomson in 1927 discovered electron diffraction and established the wave nature of light, of electron. So the son got the Nobel Prize for showing that electron had wave nature. So father got the Nobel Prize for discovering the particle electron, and his son got the Nobel Prize for showing that that same particle can show wave nature too. So this is I find this story very intriguing, and I thought I might share it with you. It's a very interesting story. So now, when we are saying that there is a wave associated with a moving particle, we have to remember that this wave cannot be a monochromatic wave. Why? Because we know that when we are talking about a particle, at any moment of time, at any instant of time, right, we can actually say that the particle exists at so and so coordinate. However, be anywhere between minus infinity to plus infinity. That cannot be the case. So instead of a single by a wave packet. And secondly, if the momentum of a particle is precisely known, then the associated wavelength would have a definite value, because we know from this formula that lambda equal to h by p. So if p, the momentum, has a fixed value, since h is a constant, then lambda would have a fixed value. Now what